In 1998, two rival teams of astronomers pointed their telescopes at dying stars billions of light years away, expecting to confirm what everyone already believed, that the expansion of the universe was gradually slowing down, that gravity was winning. Instead, they found the opposite. The universe wasn't slowing down, it was speeding up. Something invisible, something with no known source, was pushing the fabric of space apart faster and faster with every passing moment. When they checked and rechecked their data, the answer didn't change. Roughly 68% of everything that exists is made of something we cannot see, cannot touch, and can't explain. Scientists gave it a name, dark energy, but a name is not an explanation. Tonight we're going to explore what dark energy actually is, why it behaves unlike anything else in physics, and why, if left unchecked, it will tear the universe apart. If you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. To understand why the 1998 discovery was so shocking, you first need to understand what astronomers expected to find. Because they did not go looking for dark energy. Nobody was searching for it. Nobody even imagined it existed. They were trying to answer a much simpler question. How fast is the expansion of the universe slowing down? That question might sound strange. Slowing down? Why would anyone assume the expansion was slowing down? The answer is gravity. Gravity is the universal force of attraction. Every piece of matter in the universe pulls on every other piece of matter. Stars pull on planets, galaxies pull on other galaxies. All of that matter, spread across billions of light years, should be pulling the universe back together, fighting against the expansion, gradually applying the brakes. Think of it this way. Imagine tossing a ball straight up into the air. The moment the ball leaves your hand, it is moving upward. But gravity immediately starts working against it, slowing it down. The ball rises, but it rises slower and slower with every passing moment. Eventually, gravity wins. The ball reaches its peak, hangs motionless for an instant, and then falls back down. Every person who has ever thrown a ball into the sky has watched gravity win. It always wins. That is what gravity does. Now, imagine applying the same logic to the universe itself. The universe is expanding. We have known this since 1929, when the American astronomer Edwin Hubble made one of the most important discoveries in the history of science. By studying the light from distant galaxies, Hubble showed that those galaxies are moving away from us. Not just a few of them, all of them, in every direction you look. And the farther away a galaxy is, the faster it is receding. The universe is not standing still. It is growing. This was a revolutionary discovery. For most of human history, people assumed the universe was static and eternal. It had always existed. It would always exist. And it was not going anywhere. Even Albert Einstein believed this so deeply that when his own equations of general relativity, published in 1915, predicted the universe should be either expanding or contracting, he refused to accept it. He went so far as to alter his own brilliant equations to force them to describe a motionless cosmos, adding a mathematical term specifically designed to prevent the universe from changing. It took Hubble's observations to prove what Einstein's unmodified mathematics had been telling him all along. The universe was not standing still. Space was growing. Galaxies were drifting apart from one another. carried along by the stretching of space itself. We will come back to the remarkable term Einstein added, and the ironic twist that brought it back from the dead very soon. But here is the important part. If you have an expanding universe filled with matter, and matter generates gravity, and gravity pulls things together, then gravity should be slowing that expansion down. Just like the ball you threw into the air. The universe was expanding, yes, but surely it was expanding slower and slower over time as the gravitational pull of all that matter fought against the expansion, resisted it, gradually dragged it back. The great question in cosmology for decades was not whether the expansion was decelerating. Almost everyone assumed it was. The question was how much? How hard was gravity pulling on the brakes? And the answer to that question would determine nothing less than the ultimate fate of everything that exists. There were essentially three possibilities. If there was enough matter in the universe, enough gravitational pull, the expansion would eventually stop and reverse. The universe would begin to contract, falling back in on itself, collapsing until everything crashed together in a kind of reverse Big Bang that scientists called the Big Crunch. All of space, all of time, all matter and energy converging into a single point. The end of everything. If there was exactly the right amount of matter, the expansion would slow to a halt only after an infinite stretch of time, perfectly poised on a razor's edge between expansion and collapse. And if there was not enough matter, the universe would expand forever, a stretching into cold emptiness, but always decelerating. Like a ball thrown hard enough to escape Earth's gravity, drifting outward forever, but always losing speed. All three of these scenarios shared one critical assumption. The expansion was decelerating. Gravity was applying the brakes. The only question was how hard. How much was gravity slowing things down? That was the problem astronomers set out to solve in the early 1990s. And to solve it, they needed a very specific kind of tool. They needed a way to measure how fast the universe was expanding at different moments in its history. They needed to compare the expansion rate billions of years ago with the expansion rate today. If gravity was slowing things down, the universe should have been expanding faster in the distant past than it is now. The expansion rate should be decreasing over time. Measure that decrease, and you measure gravity's grip on the cosmos. To make that comparison, you need two pieces of information for any distant galaxy. You need to know how fast it is moving away from you, and you need to know how far away it is. The first part is relatively straightforward. When a galaxy is moving away from you, the light it emits gets stretched by the expansion of space. The wavelengths grow longer, shifting toward red. This is called redshift, and the amount of redshift tells you how much space has expanded while that light was traveling toward you. The second part, the distance, is much harder. Measuring distances across the universe is one of the most difficult problems in all of astronomy. You cannot stretch a tape measure to a galaxy billions of light years away. You cannot send out a signal and time how long it takes to bounce back. The distances are simply too vast. You need something else entirely. You need a cosmic ruler. Something out there in the universe whose properties allow you to calculate how far away it is without ever visiting it. The method that changed everything relies on a concept called a standard candle. Imagine standing in a dark field at night. Far away, someone holds up a lantern. You cannot tell how far away it is just by looking. But if you knew exactly how bright that lantern truly was, you could calculate the distance. A lantern of known brightness that appears very dim must be very far away. The same lantern appearing brighter must be closer. Brightness falls off predictably with distance. Double the distance, and the apparent brightness drops to 1/4. That is what astronomers mean by a standard candle. An object with a known, consistent, intrinsic brightness. Measure how bright it appears from Earth, compare that to its true brightness, and the difference tells you the distance. The challenge is finding objects that reliably produce the same luminosity every time. Stars vary wildly. Galaxies come in every size. Most cosmic objects are useless as standard candles, but it turns out nature does provide one of the best standard candles imaginable. A specific type of stellar explosion called a Type 1a supernova. And to understand why these explosions work so beautifully as cosmic distance markers, you need to understand what causes them. Stars like our Sun do not last forever. They burn through their nuclear fuel over billions of years, fusing hydrogen into helium. When a Sun-like star exhausts that fuel, it swells into a red giant, sheds its outer layers, and leaves behind a small, extraordinarily dense object called a white dwarf. A white dwarf is roughly the size of Earth, but contains about half the mass of our Sun. A single teaspoon of white dwarf material would weigh several tons. These are dead stellar cores, glowing white hot from residual heat, slowly cooling over billions of years. Now, many stars in the universe do not exist alone. They exist in binary systems. Two stars orbiting each other, locked together by mutual gravitational attraction, dancing around a common center of mass. If one of those stars is a white dwarf, and the other is a normal, still living star, something remarkable can happen. The white dwarf's intense gravity can pull matter off its companion. Gas streams away from the companion star, spirals down onto the white dwarf surface in a swirling accretion disk, and settles onto the surface, adding to its mass. Layer by layer, atom by atom, the white dwarf gets heavier, and heavier, and heavier. But there is a critical mass threshold, roughly 1.4 times the mass of our Sun. This limit is not arbitrary. It comes from fundamental physics, from the quantum mechanical behavior of electrons under extreme pressure. Below this limit, the electrons inside the white dwarf exert enough outward pressure to support the star against its own gravity. But as the white dwarf gains mass and approaches this threshold, the pressure becomes insufficient. Carbon and oxygen nuclei in its core begin to fuse in a runaway thermonuclear reaction. Not a controlled, steady burn like the fusion inside a living star. An explosion. A catastrophic, total detonation that tears the entire white dwarf apart in a matter of seconds, releasing an almost inconceivable amount of energy. The star does not partially explode. It does not leave a remnant behind. The entire object is obliterated in a single violent event. This is a Type 1a supernova. And here is the crucial detail that makes these explosions so extraordinarily valuable to astronomers. Because the explosion is triggered at roughly the same mass every time, very near 1.4 solar masses, the explosion itself is remarkably consistent. Every Type 1a supernova releases roughly the same total amount of energy. They all reach roughly the same peak luminosity. They are not perfectly identical. Small variations exist depending on the composition and exact conditions of the white dwarf. But in the early 1990s, astronomers developed a clever technique to account for those variations. They noticed that brighter Type 1a supernovae fade more slowly after reaching peak brightness, while dimmer ones fade more quickly. By carefully measuring the rate at which a supernova's light declines over the weeks following its peak, you can calibrate its true peak brightness with impressive accuracy. This relationship, called the light curve width luminosity relation, transformed type 1a supernovae from good standard candles into exquisite ones. And these explosions are staggeringly bright. At peak luminosity, a single type 1a supernova can briefly outshine its entire host galaxy. One exploding white dwarf, smaller than Earth, putting out more light for a few weeks than hundreds of billions of stars combined. This means you can spot them across enormous distances, billions of light years. You can observe these explosions in the deep past, in a younger cosmos, and use them to measure distances with a precision that no other method could match at such scales. This is exactly what two competing teams of astronomers set out to do in the 1990s. Both teams wanted to find type 1a supernova at various distances, measure their brightnesses, calculate their distances, and compare those distances to what a decelerating universe would predict. If the universe was slowing down as expected, the distant supernovae should appear at certain predictable brightnesses. The theoretical framework was solid. The predictions were clear. All they needed was the data. The first team was the Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory in California. Perlmutter had been working on this problem since the late 1980s, developing systematic methods for hunting distant supernovae in a way nobody had done before. His team pioneered a technique that was both ingenious and grueling. They would image large patches of the night sky using sensitive cameras on major telescopes, capturing thousands of faint galaxies in each exposure. Then, they would wait a few weeks and image the same patches again. By meticulously comparing the two sets of images, they could identify any new bright spots that had appeared. Tiny pinpricks of fresh light in galaxies billions of light years away. Each new point of light was a candidate supernova. Once they found a candidate, the clock started ticking. They had to rush to confirm it using spectroscopy, splitting the light into its component wavelengths to verify that the explosion was indeed a Type 1a supernova, and not some other variety of stellar death. They had to measure the redshift. They had to track how the brightness faded over the following weeks. And every step required precious observing time on some of the largest, most oversubscribed telescopes in the world. The second team was the High Redshift Supernova Search Team, led by Brian Schmidt at the Australian National University, with a young postdoctoral researcher named Adam Rees playing a crucial role in developing the data analysis pipeline. Rees wrote sophisticated code to extract the most precise possible distance measurements from the supernova observations, carefully accounting for every known source of uncertainty. The two teams used similar observational techniques, but different telescopes, different software, and somewhat different methods for analyzing the data. They were fierce competitors. They raced to find the same supernovae, raced to book the same telescope time, raced to publish their results first. But this rivalry would ultimately be one of the discovery's greatest strengths. Because when two competing teams using independent methods reach the same conclusion, it is very difficult to argue the conclusion is wrong. Finding distant supernovae is extraordinarily difficult work. Type 1. A supernovae are rare events. A typical galaxy might produce one every few centuries. You cannot predict when or where one will occur. When one does appear, it brightens rapidly over a period of roughly 2 to 3 weeks, reaches its peak luminosity, and then fades steadily over the following months. You have a narrow window to catch it near peak, confirm its type, measure its redshift, and carefully track its light curve as it declines. Miss the window, and the data is incomplete or useless. Both teams spent years accumulating their samples, building their collections supernova by supernova, observation by painstaking observation, slowly assembling enough data points scattered across billions of light years to draw statistically meaningful conclusions about how the expansion of the universe has changed over time. By 1997 and early 1998, both teams had accumulated enough well-measured Type 1a supernovae at sufficient distances to begin drawing conclusions. They had dozens of carefully calibrated supernovae spanning billions of light years of cosmic history. They had nearby supernovae for comparison. They had rigorous calibrations, exhaustive systematic checks, and multiple independent methods for analyzing the data. The stage was set for what should have been a clean, satisfying confirmation. Yes, the universe is decelerating. Here is how much. Here is the fate of the cosmos. The results were not what anyone expected. The distant supernovae were too dim, not by a dramatic amount, not wildly, obviously wrong, but consistently, persistently, unmistakably dimmer than any decelerating model of the universe predicted. Both teams found the same thing. The supernovae at high redshift, the ones whose light had been traveling for billions of years across the expanding cosmos, appeared fainter than they should have. And in the logic of standard candles, dimmer means farther away. The supernovae were farther from us than a decelerating universe would allow. The teams immediately suspected errors. This is what careful scientists do. When your data gives you a result you did not expect, a result that contradicts decades of theoretical expectation, your first instinct should be to question the data, not to believe it. Both teams scrutinized their observations with relentless care, hunting for anything that could explain the anomaly. Maybe the distant supernovae were being dimmed by cosmic dust. Dust floating in intergalactic space could absorb and scatter light, making objects appear fainter and therefore apparently more distant than they actually are. But dust does not just dim light, it also reddens it. If cosmic dust were responsible for the unexpected dimming, the distant supernovae should also appear redder than expected. The teams checked carefully and found no excess reddening that matched the amount of dimming they observed. Dust could not explain the result. Maybe distant Type 1a supernovae were intrinsically different from nearby ones. Perhaps supernova that exploded billions of years ago, when the universe was younger and the chemical composition of stars was somewhat different, produced slightly less light. Both teams investigated this possibility thoroughly. They compared the light curves, the spectra, and the host galaxy environments of their distant supernovae with well-studied nearby examples. They found no systematic difference large enough to account for the observed dimming. The distant explosions behaved the same way nearby ones did. They were simply too faint. After exhausting every plausible source of error, after checking and rechecking every step of the analysis, after independently arriving at the same result without sharing their data, both teams reached the same conclusion. A conclusion so unexpected, so profoundly counterintuitive, so contrary to everything cosmologists believed about how gravity governs the evolution of the universe, that neither team published immediately. They agonized. They double-checked. They worried they'd made an error that would humiliate them before the entire scientific community. But the data held. The distant supernovae were genuinely farther away than any decelerating model predicted. And there was only one explanation that fit. The expansion of the universe is not slowing down. It is speeding up. The cosmos is accelerating. Both teams announced their results in 1998. Perlmutter and his supernova cosmology project. Schmidt, Rees, and the High Redshift Supernova Search Team. Two independent groups, using different telescopes, different data, different analysis methods, reaching the same extraordinary conclusion. The expansion of the universe is accelerating. Something out there is overpowering gravity at the largest scales. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for this discovery. It was recognized as one of the most important findings in the history of science. Think about what this means. Go back to the ball you threw into the air. You threw it upward, and instead of slowing down, reaching a peak, and falling back into your hand, the ball accelerated away from you. It flew faster and faster, as though some invisible force were pushing it from below. Not just coasting. Not just resisting gravity a little longer than expected. Actively speeding up. Defying the pull of Earth. That is what the universe is doing. Except, it is not a ball in a hand. It is every galaxy in the observable cosmos, and the force pushing them apart is something we had never detected before. Something we still struggle to explain. Scientists name this something dark energy. And it is important to understand from the start that dark energy is not what most people picture when they hear the word energy. It is not a beam of light. It is not a force field. It is not a type of radiation shooting across space. It is a property of space itself, something woven into the fabric of the cosmos, exerting a kind of repulsive pressure that drives the expansion to accelerate. Let me make sure you understand what accelerating expansion actually means physically, because it is easy to get the wrong picture in your head. Galaxies are not flying through space like rockets fired outward from some central point. They are not objects racing away from us through a fixed, static background of empty space. What is happening is more fundamental than that, and far stranger. Space itself is stretching. The actual distance between points in the universe is growing, not because objects are moving through space, but because the space between them is expanding. Imagine drawing dots on the surface of a balloon, then slowly inflating it. As the balloon expands, every dot moves away from every other dot. Not because the dots are sliding across the rubber. The dots are staying perfectly still on the surface, but the surface itself is growing. The rubber between the dots is stretching, creating more distance between them with every moment. And the farther apart two dots are, the faster the distance between them increases, because there is more rubber in between to stretch. This is the expansion of the universe. Space is the rubber. Galaxies are the dots. And the rubber is stretching everywhere, at every point, simultaneously. Now here is what makes the 1998 discovery so profoundly unsettling. Everyone expected the stretching to be slowing down. The mutual gravitational attraction of all the matter on the balloon's surface should have been resisting the inflation, working against it, pulling the rubber back together. But instead, the stretching is getting faster. The balloon is inflating more rapidly with every passing moment. Something is actively driving the rubber to stretch harder and harder, overwhelming gravity, and it shows no sign of stopping. Before we go any further, there is an important distinction that needs to be made clearly, because the terminology causes enormous confusion. Dark energy is not dark matter. These are two entirely separate phenomena. They share only the word dark, which in both cases simply means we cannot directly see it. That is where the similarity ends. Dark matter is matter. It has mass. It exerts gravitational attraction. It clumps together and forms structures. We know it exists because galaxies rotate too fast to be held together by the visible matter they contain. Stars in the outer regions of spiral galaxies orbit at speeds that should fling them out into intergalactic space, yet something invisible provides the extra gravitational pull to hold them in place. That something is dark matter. It interacts with gravity. It clusters around galaxies in enormous invisible halos. It played a critical role in shaping the large-scale structure of the cosmos. It behaves, in most important respects, the way ordinary matter does, except that it does not interact with light. You cannot see it, but it pulls things together. Dark matter makes up about 27% of the total energy content of the universe. Dark energy is the opposite in almost every fundamental way. It does not clump. It does not form structures. It does not gather around galaxies or stars or planets. It is spread uniformly throughout all of space. And most critically, it does not pull things together. It pushes them apart. Dark energy is not a form of matter. It is a property of the vacuum, of empty space itself, and it is what drives the accelerating expansion of the universe. Dark energy accounts for about 68% of the total energy content of the universe, making it the single most dominant component of everything that exists. These two phenomena, dark matter and dark energy, are as fundamentally different as gravity and temperature. They share a word. That is all. Now consider what all of this means. Look around you. Everything you have ever touched, every object you have ever held, every person you have ever known, every star you have ever seen scattered across the night sky, all of the ordinary matter in the entire observable universe, every atom of hydrogen, every molecule of water, every grain of sand on every beach of every planet orbiting every star, all of it represents roughly 5% of what exists. 5%. The remaining 95% is made of things we cannot directly detect. 27% is dark matter, which at least behaves in ways we can model and predict. And 68% is dark energy, a phenomenon so fundamentally strange that after more than a quarter century of intensive research, involving thousands of physicists and billions of dollars in experiments, we still cannot explain what it is or why it has the value it has. Before 1998, cosmologists believed they were approaching a complete picture of the universe. They understood that it was expanding. They had a robust and well-tested model of the Big Bang. They understood the nuclear physics that produced light elements like hydrogen and helium in the first few minutes of cosmic history. They had detected the cosmic microwave background radiation, the faint, ancient afterglow of the Big Bang that fills all of space with a dim glow of microwave light. The framework was coming together beautifully. The universe was made of matter and radiation. Matter generated gravity. Gravity governed how the cosmos evolved over billions of years. It was a clean, satisfying, increasingly precise picture. Then the supernova data shattered that picture. The universe was not behaving the way matter and gravity alone demanded. Something else was at work. Something completely outside the existing framework. Something no theorist had confidently predicted from first principles. Something that did not fit into any category physicists had prepared. Something that made the universe stranger than anyone had dared to imagine. The discovery raised questions that have haunted physics ever since. What is dark energy? Is it a permanent, unchanging property of empty space, built into the architecture of the cosmos from the very beginning? Or is it something dynamic, a field that evolves over time, shifting in strength as the universe ages? Why does it have the particular value it has? Why not a million times stronger? Why not zero? Where does this energy come from? What generates it? And could it change in the future, growing stronger, growing weaker, or transforming into something we have not yet imagined? And perhaps the most unsettling question of all, what does dark energy mean for the future of the universe? If the expansion is accelerating now, what happens as that acceleration continues, unchecked, across billions and trillions of years? If something is already overpowering gravity on the grandest scales, what happens when its influence grows stronger still? Will galaxies recede from one another so rapidly that no light from one can ever reach another? Will the universe become an unimaginable, cold, empty darkness where every galaxy drifts in total isolation? Or could something even more violent happen? Could the acceleration grow so fierce that it tears apart not just the spaces between galaxies, but galaxies themselves, then solar systems, then planets, then molecules, then atoms? These questions didn't exist before 1998. The discovery of accelerating expansion did not simply add a footnote to the textbook of cosmology. It tore out entire chapters and replaced them with blank pages. It revealed that the dominant force shaping the evolution of the universe at the largest scales is not gravity, which we have studied for centuries and understand deeply, but something else entirely. Something that fills every cubic centimeter of empty space with a peculiar repulsive pressure. Something that has been quietly winning its battle against gravity for billions of years, while we had no idea it was even there. For most of human history, we believe we understood the basic ingredients of reality: matter, energy, light, gravity. We had equations that described them. We had models that predicted their behavior. We had a growing confidence that the fundamental picture was nearly complete. Then, two teams of astronomers observed dying stars in the distant universe and discovered that 68% of everything that exists is made of something we cannot name, cannot detect directly, and cannot explain. That is the mystery at the heart of modern cosmology. And understanding what we know about it, what we suspect, and what it means for the ultimate fate of every atom in existence is exactly where we are heading next. So something is pushing the universe apart. Something is overpowering gravity at the largest scales, stretching the fabric of space faster and faster with every passing moment, driving galaxies away from one another at an ever-increasing rate. The supernova observations confirmed it. The acceleration is real, but confirmation only deepened the mystery. What is doing this? What kind of energy could possibly fill all of space, resist the pull of gravity, and cause the expansion of the cosmos to speed up rather than slow down? Physicists had a candidate almost immediately. And it was not a new idea. It was an old idea, one that had been proposed, abandoned, ridiculed, and nearly forgotten over the course of the 20th century. It had been sitting quietly in the equations of general relativity for over 80 years, waiting for someone to need it. Its name is the cosmological constant, and its history is one of the strangest in all of physics. The story begins with Albert Einstein. In 1915, Einstein published his general theory of relativity, one of the greatest intellectual achievements in human history. General relativity replaced Newton's picture of gravity as a force acting between objects with something far more profound: Gravity, Einstein showed, is not a force at all. It is the curvature of spacetime. Matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. Massive objects like stars and planets warp the geometry of space and time around them, and other objects follow the curved paths that this warped geometry creates. A planet does not orbit a star because the star is pulling on it with an invisible rope. The planet orbits because the star has curved the space-time around it, and the planet is following the straightest possible path through that curved geometry. This framework made precise, testable predictions. The bending of light near massive objects, confirmed in 1919. Time running slower in stronger gravitational fields, confirmed with atomic clocks. Gravitational waves, directly detected in 2015. General relativity has passed every experimental test thrown at it. But in 1917, just 2 years after publishing his masterwork, Einstein ran into a problem. When he applied his equations to the universe as a whole, treating the cosmos as a uniform distribution of matter, filling all of space, the equations told him something he did not want to hear. The universe could not stand still. His equations demanded that a universe filled with matter must either be expanding or contracting. A static, unchanging, perfectly balanced universe was not a stable solution. It was like trying to balance a ball on the tip of a needle. Any tiny disturbance, and it falls. This troubled Einstein deeply. In 1917, the prevailing view was that the universe was static and eternal. The night sky looked the same century after century. The idea that the universe itself might be expanding or contracting struck most people, Einstein included, as absurd. So Einstein did something remarkable. He modified his own equations. He added a new term, a mathematical constant, that could counterbalance the gravitational attraction of matter and hold the universe perfectly still. He called it the cosmological constant, represented by the Greek letter lambda. The cosmological constant acted as a kind of anti-gravity, a gentle outward push woven into the very fabric of space-time that exactly balanced the inward pull of matter. With lambda carefully tuned to precisely the right value, Einstein's equations could describe a static, eternal, unchanging universe. The cosmos sat in perfect equilibrium. Gravity pulled inward. Lambda pushed outward. The two forces balanced, and the universe remained motionless. Einstein was not entirely happy with this solution. The cosmological constant felt artificial. It was not derived from any deeper physical principle. It was simply grafted onto the equations to produce the answer Einstein wanted. It was a fix, a patch, a mathematical band-aid applied because the equations gave an uncomfortable result. But it worked. And in 1917, nobody had any evidence that the universe was doing anything other than sitting still. Then came the observations that changed everything. In 1929, Hubble's measurements confirmed what Einstein's unmodified equations had predicted all along. The universe is expanding. Every galaxy is receding from every other galaxy, carried by the stretching of space. The cosmological constant had been entirely unnecessary. Einstein had invented a mathematical patch to suppress a prediction that turned out to be gloriously correct. According to accounts from physicists who knew him, he came to regard it as his greatest blunder. He had missed the chance to predict one of the most profound discoveries in science because he lacked the courage to trust his own equations. For the rest of the 20th century, the cosmological constant was treated as a cautionary tale, a lesson about the danger of letting assumptions override mathematics. Most physicists set lambda to 0, and forgot about it. It served no purpose. The universe was expanding. Gravity was decelerating that expansion. The cosmological constant was a relic, an embarrassment, a discarded artifact of Einstein's one great mistake. Then came 1998. The supernova teams discovered that the expansion of the universe is not decelerating, it is accelerating. And suddenly, physicists needed exactly the thing Einstein had introduced and abandoned. They needed something that pushes space apart. They needed a cosmological constant. The resurrection of lambda is one of the great ironies in the history of physics. Einstein added it to prevent the universe from expanding. He abandoned it when expansion was discovered, and decades later, it returned to explain why the expansion is speeding up. Einstein was right to add it, but for completely the wrong reason, and he was wrong to remove it even though removing it seemed perfectly sensible at the time. But here is the critical question. If the cosmological constant is real, if lambda is not 0, what does it physically represent? Einstein introduced it as a mathematical term, a number you plug into the equations. But physics demands more than mathematics. If lambda is a real feature of the universe, it must correspond to something physical. It must have a cause, it must come from somewhere. The answer, or at least the leading candidate for an answer, is vacuum energy. This is one of the most counterintuitive concepts in all of physics, and understanding it is essential to understanding dark energy. So let me walk you through it carefully. When you look at a region of space that contains nothing, no matter, no radiation, no particles of any kind, you might assume that region is truly empty. There is nothing there. The energy of that region is 0. It is a void in the most absolute sense of the word. But quantum mechanics tells us this picture is completely wrong. Empty space is not empty. It cannot be. The uncertainty principle, one of the foundational rules of quantum physics, forbids perfect emptiness. The uncertainty principle says that certain pairs of physical quantities cannot both be precisely 0 simultaneously. You cannot know both the position and momentum of a particle with perfect certainty. And you cannot have a quantum field that is perfectly exactly 0 everywhere with 0 energy. In modern physics, the fundamental ingredients of reality are not particles, but fields. There is an electron field permeating all of space. When that field is excited, we observe an electron. There is a photon field. Excitations in it are what we perceive as light. Every fundamental particle corresponds to a field that fills the entire universe, even in the emptiest vacuum imaginable. Now, quantum mechanics says these fields cannot sit perfectly still. They must fluctuate. Even in a vacuum state, the lowest possible energy state of a field, the field vibrates. These are called 0-point fluctuations, the irreducible, unavoidable jittering of quantum fields, even when nothing is happening, even when no particles are present, even in the coldest, emptiest region of space you can imagine. The fields tremble, they oscillate, and these oscillations carry energy. This is vacuum energy, the energy of empty space, the energy that remains even after you have removed every particle, every photon, every speck of matter. Even then, the quantum fields are vibrating, and those vibrations contribute energy to the vacuum. Empty space, according to quantum mechanics, is not empty. It is a seething ocean of quantum fluctuations, and that ocean has energy. This is not speculation. We have experimental evidence that vacuum energy is real. The most famous demonstration is the Casimir effect. first predicted by the Dutch physicist Hendrik Casimir in 1948, and confirmed experimentally decades later with increasing precision. The Casimir effect works like this. Take two flat, uncharged, perfectly conducting metal plates and place them very close together in a vacuum, separated by a tiny gap. Between the plates, only certain wavelengths of quantum fluctuations can fit. The gap acts like a filter, restricting which vibrations are possible inside it, but outside the plates, there is no such restriction. All wavelengths of quantum fluctuations are present. This creates an imbalance. There are more fluctuations pushing on the outside of the plates than on the inside. The result is a tiny but measurable force pushing the plates together. This force has been measured. It matches the theoretical prediction. Vacuum energy is real. Empty space genuinely contains energy. Now, here is where things get strange. And here is where the cosmological constant enters the picture in a physical, tangible way, rather than as a mathematical abstraction. In Einstein's general relativity, gravity responds to energy. All forms of energy curve space-time. This is a fundamental principle of the theory. If the vacuum of space contains energy, then that energy must curve space-time. It must have gravitational effects. You cannot have energy that gravity ignores. General relativity does not allow it. But vacuum energy is unlike any other form of energy we encounter in daily life. It does not clump. It does not flow. It does not radiate. It is the same everywhere and at all times. Every cubic centimeter of space contains the same amount of vacuum energy, whether that space is between galaxies or inside your living room. And because it is a property of space itself, as the universe expands and creates more space, more vacuum energy appears. The density stays the same, but the total amount grows because there is more space to contain it. This leads to a bizarre property. Vacuum energy has negative pressure, and negative pressure in general relativity does something extraordinary. It causes gravity to push rather than pull. This is the single most important concept in understanding dark energy, and it is worth taking the time to grasp it properly. In general relativity, gravity is not generated by mass alone. It is generated by energy and pressure together. This is a critical departure from Newton's picture of gravity. Newton said that mass attracts mass, but Einstein showed that the full source of gravity includes both energy density and pressure. Specifically, in Einstein's equations, the gravitational effect of any substance depends on its energy density plus 3 times its pressure. If both energy density and pressure are positive, as they are for ordinary matter and radiation, the gravitational effect is attractive. Things pull together. This is the gravity we know and experience every day. But if the pressure is negative, and if it is sufficiently negative, something remarkable happens. The combination of energy density plus 3 times the pressure can become negative overall, and when that combination goes negative, gravity reverses. Instead of pulling things together, it pushes them apart. Gravity becomes repulsive. For the cosmological constant, the pressure is not just slightly negative, it is as negative as it can possibly be. The pressure of vacuum energy equals its energy density but with a negative sign. This means the energy density plus 3 times the pressure gives a result that is strongly negative. Twice the energy density but in the repulsive direction. Vacuum energy does not just fail to attract, it actively repels. It pushes space apart. This is the physical mechanism behind the accelerating expansion of the universe. Every cubic centimeter of empty space contains a tiny amount of vacuum energy. That energy exerts a negative pressure. That negative pressure, through Einstein's equations, generates a repulsive gravitational effect. On small scales, this effect is negligible. It is utterly swamped by the attractive gravity of ordinary matter. You will never notice vacuum energy holding your coffee cup. The gravitational pull of the atoms in your cup, in the table beneath it, in the earth below, is incomparably stronger than the feeble repulsive push of vacuum energy in the space around it. But on cosmic scales, things are different. As you look at larger and larger volumes of space, the total amount of matter stays roughly the same. Galaxies are scattered through space, but the density of matter decreases as the universe expands. The matter thins out, but vacuum energy does not thin out. Its density is constant. Every new cubic centimeter of space that the expansion creates comes with its own vacuum energy, at the same density as everywhere else. Matter dilutes. Vacuum energy does not. This means there is a crossover point. Early in the universe's history, when everything was packed closely together, the density of matter was enormous. Gravity dominated. The expansion decelerated, just as everyone expected. But as the universe expanded and matter spread thinner and thinner, the constant density of vacuum energy eventually caught up. A few billion years ago, the density of matter dropped below the density of vacuum energy. And at that moment, the repulsive push of the vacuum began to win. The expansion stopped decelerating and started accelerating. We are living in the era when dark energy has taken control of the universe's evolution. This picture is elegant. It is consistent with the supernova data. It is consistent with other independent observations, including measurements of the cosmic microwave background and the large-scale distribution of galaxies. The cosmological constant, lambda, interpreted as the energy of the quantum vacuum, provides a clean, simple explanation for the accelerating expansion. One number, one constant, woven into the fabric of spacetime, explaining the biggest mystery in modern cosmology. There's just one enormous, devastating problem. The predicted value is catastrophically wrong. This is the cosmological constant problem, and it is not an exaggeration to call it the most embarrassing failure in the history of theoretical physics. When physicists use quantum field theory, the extraordinarily successful framework that describes particle physics, to calculate how much energy the vacuum should contain, they get a number. And that number is not just a little bit off. It is not wrong by a factor of 2, or 10, or even 1,000,000. It is wrong by a factor of 10 to the 120th power. That is a 1 followed by 120 zeros. It's the largest discrepancy between theory and observation in the entire history of science. Let me try to convey how absurd this mismatch is. In most areas of physics, a prediction that is wrong by a factor of 2 is considered a rough approximation. Wrong by a factor of 10, and you have clearly missed something important. Wrong by a factor of 100, and your theory is probably fundamentally flawed. Wrong by 10 to the 120th power, and something has gone so spectacularly wrong that the failure transcends ordinary error. It is not a mistake in calculation. It is not a missing correction. It is a chasm so vast between prediction and reality that it suggests we are missing something absolutely fundamental about how the universe works. Here's where the problem comes from. In quantum field theory, every quantum field contributes to the vacuum energy. The electron field contributes. The photon field contributes. The quark fields contribute. The gluon field contributes. Every field in the standard model of particle physics, the theory describing all known fundamental particles and 3 of the 4 fundamental forces, makes its own contribution to the energy of empty space. Each field's contribution depends on the energy scales at which it operates. When you add up all the contributions from all known fields, carrying the calculation up to the energy scale where we believe our current theories remain valid, you get an enormous number. The predicted vacuum energy density is fantastically large. If the vacuum truly had this much energy, the repulsive gravitational effect would be so overwhelming that no structures could ever form. No galaxies, no stars, no planets, no atoms. The universe would have been ripped apart in its earliest moments, expanding so violently that matter could never clump together under gravity. Nothing resembling the cosmos we observe could exist. But the universe obviously does exist. Stars shine. Galaxies hold together. You're sitting here hearing these words on a planet orbiting a stable star in a galaxy that has been around for over 13 billion years. The vacuum energy that actually exists, the dark energy we measure through the accelerating expansion, is incredibly small. Not zero, but extremely, almost absurdly small, compared to what quantum field theory predicts. The observed value of the cosmological constant is roughly 10 to the 120th power times smaller than the predicted value. It is as if quantum mechanics is shouting that the vacuum energy should be enormous, an overwhelmingly dominant feature of the cosmos, and the universe is quietly whispering back that actually, it is almost nothing. Almost zero, but not quite zero. And that last detail, the not quite zero part, makes everything worse. If the observed vacuum energy were exactly zero, physicists might hope to find some deep symmetry, some elegant principle that forces all the contributions to cancel perfectly. Zero is a special number. Symmetries produce zeros. If you could find a reason for perfect cancellation, the problem would be solved. Difficult perhaps, but conceptually clean. But the observed value is not zero. It is a tiny, positive number. Something cancels the predicted vacuum energy almost perfectly, eliminating 120 orders of magnitude worth of energy, but leaves behind a minuscule residual. The cancellation is nearly exact, but not quite. This is exquisitely fine-tuned. Imagine two numbers, each with 120 digits, that nearly cancel when you subtract one from the other. They agree on the first 119 digits and differ only on the last one. That is the level of cancellation required to produce the cosmological constant we observe. And nobody knows what mechanism could possibly produce such absurdly precise cancellation. This is not merely a gap in our understanding, this is a crisis. The cosmological constant problem sits at the intersection of the two most successful theories in all of physics, general relativity and quantum field theory, and reveals that they are profoundly incompatible when it comes to the energy of the vacuum. General relativity says vacuum energy must gravitate. Quantum field theory says the vacuum must contain enormous energy. Together, they predict a universe that looks nothing like the one we live in. Something fundamental is missing from our understanding. Either quantum field theory is calculating vacuum energy incorrectly, or general relativity is responding to vacuum energy differently than we think. Or there is some unknown mechanism, some deep principle of nature that we have not yet discovered, that cancels almost all of the vacuum energy and leaves behind only the tiny residual we observe. Physicists have spent decades searching for such a mechanism, and they have not found one. Supersymmetry, a theoretical framework proposing that every known particle has an as-yet undiscovered partner particle, was once considered a promising avenue. In a supersymmetric universe, the contributions from particles and their partners would partially cancel, reducing the predicted vacuum energy. But supersymmetry does not produce perfect cancellation unless it is an exact symmetry of nature. And we know supersymmetry, if it exists at all, must be a broken symmetry because the partner particles have never been detected. Broken supersymmetry reduces the discrepancy but does not come close to eliminating it. You might reduce the mismatch from 10 to the 120th power to 10 to the 60th power. Better, but still catastrophically wrong. Some physicists have turned to a more controversial idea, the anthropic principle. The reasoning goes like this. If the cosmological constant were much larger than its observed value, the universe would expand so rapidly that matter could never clump together. No galaxies, no stars, no planets, no life. If the cosmological constant were much more negative, the universe would have collapsed long ago. Again, no life. Only a universe with a cosmological constant in a very narrow range can produce observers capable of measuring it. So perhaps the cosmological constant has the value it does not because of some deep physical principle, but simply because we exist. In the vast landscape of possible universes predicted by certain versions of string theory, each with different values of the cosmological constant, most are sterile, uninhabitable, empty, but a tiny fraction have values compatible with life. We necessarily find ourselves in one of those. This is anthropic reasoning, and many physicists find it deeply unsatisfying. It replaces the question of why the cosmological constant has its value with the answer that it simply must, because otherwise we would not be here to ask. Some physicists accept it, others regard it as giving up. The debate continues. There is another approach to the problem. Perhaps the issue lies not in the cancellation mechanism, but in how we calculate vacuum energy in the first place. Perhaps the naive calculation, simply adding up contributions from all quantum fields, is not the right procedure. Perhaps gravity does not respond to vacuum energy in the straightforward way general relativity assumes. Some physicists have proposed modifications to general relativity that would make gravity insensitive to vacuum energy at large scales, allowing the vacuum to contain as much energy as quantum mechanics demands, without producing the catastrophic expansion that standard theory predicts. These proposals are interesting but face severe challenges. Any modification to general relativity must be consistent with the enormous body of observational evidence supporting it. You cannot simply change the equations of gravity to fix one problem without checking that the change does not break 100 things that already work. There is also the possibility that we are simply missing something big. Something fundamental about the relationship between quantum mechanics and gravity that no existing framework captures. The cosmological constant problem may be a symptom of our incomplete understanding, a signpost pointing toward whatever theory will eventually unify quantum mechanics and general relativity into a single coherent framework. A theory of quantum gravity might resolve the problem by revealing how vacuum energy really behaves at the deepest level, in ways that neither quantum field theory alone nor general relativity alone can describe. But for now, the problem stands. The cosmological constant, lambda, is the simplest and most successful description of dark energy we have. It fits the observational data beautifully. It explains the accelerating expansion. It is consistent with every measurement we have made, and yet we cannot explain why it has the value it does. We cannot derive it from first principles. We cannot reconcile the observed value with what our best theory of particle physics predicts. Think about what this means. The most successful description of the dominant component of the universe, the thing that makes up 68% of everything that exists, the force that will determine the ultimate fate of every galaxy and every star, is a single number that we can measure but cannot explain. We know what it does, we know how much of it there is. We can describe its effects with exquisite mathematical precision, but we do not know what it is. We do not know where it comes from. We do not know why it is not 10 to the 120th power times larger. Einstein introduced the cosmological constant to solve a problem that did not exist, then threw it away when the real answer appeared. Decades later, the universe dragged it back from the grave, dressed it in the robes of vacuum energy, and handed it to a baffled physics community with a message that seemed to say, "You cannot ignore me, you cannot explain me, and you cannot make your theories agree on my value by a margin of 120 orders of magnitude. Deal with that." The cosmological constant problem is not just an academic curiosity, it is a fundamental crack in the foundation of modern physics. It tells us that something deep and important about the relationship between gravity and quantum mechanics remains hidden. It tells us that the universe operates according to rules we have not yet discovered, and it raises an unsettling possibility. Maybe the cosmological constant is the wrong answer entirely. Maybe dark energy is not a constant at all. Maybe it is something dynamic, something that changes over time, something richer and stranger than a simple number fixed forever in the equations of general relativity. That possibility leads us somewhere entirely new. Because if dark energy is not constant, if its strength can change, then the future of the universe becomes far less certain and far more terrifying than a simple cosmological constant would allow. The cosmological constant is the simplest possible explanation for dark energy. One number, fixed, unchanging. The same value today as it was 10 billion years ago, the same value it will have 10 billion years from now. A permanent feature of space-time, woven into the architecture of reality from the very beginning. If the cosmological constant is the correct answer, then dark energy is boring, at least in the sense that it never does anything different. It just sits there, constant and uniform, pushing space apart at the same steady rate forever. But what if dark energy is not constant? What if it changes over time? What if the energy filling empty space is not a fixed property of the vacuum, but something dynamic, something alive in the physical sense? A field that evolves, shifts in strength, and could behave very differently in the future than it does today. This is not idle speculation. It is a possibility taken seriously by many physicists, and it leads to futures for the universe that range from profoundly lonely to genuinely terrifying. The idea of a dynamic dark energy has a name. It is called quintessence. The word comes from ancient philosophy. Aristotle believed that in addition to the four classical elements, earth, water, air, and fire, there existed a fifth element, a quinta essentia, that made up the heavens and was fundamentally different from the substances found on Earth. Modern physicists borrowed the name for a concept that is fundamentally different from the cosmological constant. A dark energy that is not fixed but fluid, not eternal but evolving. To understand quintessence, you need to understand the concept of a scalar field. This is a term from physics that sounds more intimidating than it actually is. A scalar field is simply a quantity that has a value at every point in space. temperature is a good everyday example. At every location in a room, the air has a temperature. That temperature can vary from place to place and change over time. Near the heater, the air is warm. Near the window, it might be cooler. The temperature field fills the room, and its value at any given point can shift as conditions change. A scalar field in physics is the same idea applied to fundamental quantities. It fills all of space, and its value can evolve over time. The most famous scalar field in physics is the Higgs field, which was confirmed by the discovery of the Higgs boson at the Large Hadron Collider in 2012. The Higgs field permeates all of space, and its interaction with particles is what gives those particles their mass. Before the Higgs boson was discovered, the Higgs field was a theoretical construct that many physicists believed in because it solved critical problems in particle physics. Now we know it is real. Scalar fields are not abstractions. They are physical features of the universe. Quintessence proposes that dark energy is caused by a similar kind of field. A scalar field filling all of space, but one whose energy density is not locked at a fixed value. Instead, the field slowly rolls along its energy landscape. And as it does, the amount of energy it contributes to each cubic centimeter of space changes. The field is dynamic. It evolves. The dark energy we observe today is the field's energy at this particular moment in cosmic history. But that energy might have been different in the past, and could be different in the future. This distinction between the cosmological constant and quintessence might sound subtle, but its consequences are enormous. And to understand why, you need to grasp a single number. It is called the equation of state parameter, and physicists denote it with the letter W. This number describes the relationship between the pressure and the energy density of whatever substance is driving the expansion. It is, in a very real sense, the number that determines the fate of the universe. For ordinary matter, like the atoms that make up stars and planets and people, W equals 0. Matter has energy density but essentially no pressure in the cosmological sense. For radiation, like photons of light, W equals 1/3. Radiation has positive pressure proportional to its energy density. Both matter and radiation produce attractive gravity. They slow the expansion down. For a cosmological constant, W equals exactly -1. The pressure is negative and equal in magnitude to the energy density. This is the specific relationship that produces the repulsive gravitational effect, driving the accelerating expansion. And crucially, for a cosmological constant, W never changes. It is -1 today. It was -1 10 billion years ago. It will be -1 10 billion years from now. Always and forever, precisely -1. For quintessence, W can differ from -1. It might be -0.8, or -0.9, or -1.1. And it can change over time. Maybe W was closer to 0 in the early universe and has been decreasing toward -1 as the field evolved. Maybe it will continue changing in the future. The exact value and its evolution depend on the shape of the quintessence field's energy landscape. The mathematical function describing how the field's energy varies as the field changes. Different energy landscapes produce different behaviors for W, which in turn produce different futures for the cosmos. This is why measuring W with extreme precision is one of the most important goals in modern cosmology. If observations determine that W equals exactly -1 at all times, with no variation, then the cosmological constant wins. Dark energy is a fixed property of the vacuum. Case closed, at least observationally. But if W differs from -1 by even a tiny amount, or if it changes over time, the cosmological constant is ruled out. Dark energy must be something dynamic, something like quintessence, and that opens the door to futures that are very different from what a cosmological constant would produce. Let us explore those futures, because the value of W does not merely determine an abstract number in a physicist's equation. It determines how the universe ends. Everything. Every galaxy, every star, every planet, every atom. The fate of all of it hinges on this one number. Start with the scenario where W equals exactly -1, the cosmological constant. In this future, dark energy maintains its current strength forever. It does not grow stronger. It does not weaken. The density of vacuum energy remains exactly what it is today, filling every cubic centimeter of space with the same tiny amount of repulsive energy for all of eternity. In this scenario, the universe expands forever, and the expansion accelerates forever. But because the dark energy density is constant, the acceleration reaches a kind of steady state. The universe does not explode apart in a sudden cataclysm. Instead, it stretches out gradually, relentlessly, over unimaginable timescales. Here is what happens. Over the next few billion years, the expansion carries distant galaxies farther and farther away from us. The space between galaxy clusters grows. Light from those distant clusters gets stretched to longer and longer wavelengths, redshifted further and further toward the infrared, toward radio waves, until eventually it stretches beyond any wavelength we could detect. One by one, distant galaxies fade from view. Not because they stop shining, but because the expansion of space stretches their light into invisibility. The Milky Way is gravitationally bound to the Andromeda Galaxy and a few dozen smaller companions in our local group. Gravity holds this small collection of galaxies together against the expansion. In about 4.5 billion years, the Milky Way and Andromeda will merge into a single, large, elliptical galaxy. But beyond the local group, every other galaxy cluster drifts away, carried by the expanding space between us. Eventually, roughly 100 billion years from now, every galaxy cluster beyond our own will have crossed the cosmic horizon. The light they emit will never reach us. We will be completely, utterly isolated, an island of gravitationally bound matter, floating in an infinite, empty, expanding void. From inside this island galaxy, the universe will appear profoundly different. A civilization living 100 billion years from now would see nothing beyond their own galaxy. The cosmic microwave background will have been stretched to undetectable wavelengths. There will be no distant galaxies to observe, no evidence of the Big Bang. The universe will look small, dark, and static. Any beings alive at that time might conclude, just as humans once did, that their galaxy is all that exists. The expanding universe would have erased its own history. Inside that isolated galaxy, stars continue to burn, but not forever. Eventually, the raw material for star formation runs out. The existing stars burn through their fuel one by one. Massive blue stars die first. Stars like our Sun burn for roughly 10 billion years. Red dwarfs, extraordinarily frugal with their fuel, can burn for 10 trillion years or more. But eventually, even the red dwarfs exhaust their fuel. The galaxy goes dark. What remains is a graveyard of stellar corpses. White dwarfs slowly cooling into invisibility. Neutron stars spinning down. Black holes sitting silently in the darkness. Over truly enormous timescales, even these remnants decay. Protons might be unstable, with a half-life of perhaps 10 to the 40 years. If so, all ordinary matter will slowly disintegrate. The solid universe evaporates. The last object standing will be black holes. But even black holes do not last forever. Through Hawking radiation, they slowly lose mass. A supermassive black hole would take perhaps 10 to the 100th years to evaporate. But given enough time, even the largest black holes dissolve into faint radiation. After the last black hole evaporates, there is nothing left but a thin, cooling bath of radiation and scattered subatomic particles spread across a universe so vast and so empty that no two particles will ever interact again. The temperature of the universe asymptotically approaches absolute zero, but never quite reaches it. This is heat death, the state of maximum entropy. No structure, no complexity, no processes, no change, just an infinite, dark, cold, expanding emptiness that persists forever. Not for trillions of years, not for trillions of years, forever. An eternity of nothing. That is the future if W equals -1. It is bleak, it is final, but it is gentle. The universe does not end in violence, it ends in silence. A slow fade to black, stretched across timescales, so long that human minds cannot meaningfully comprehend them. Now let us consider the alternative. What if W is less than -1? What if dark energy is not constant but growing stronger over time? What if the repulsive pressure of empty space is increasing, accelerating the acceleration, pushing harder and harder with every passing moment? This scenario has a name. It is called phantom energy, and its consequences are not gentle. They are catastrophic. The concept was explored in detail by the physicist Robert Caldwell and his colleagues in a landmark paper published in 2003. Caldwell asked a simple question. What happens if the equation of state parameter W is less than -1? Not by much. Perhaps -1.1, perhaps -1.5. The precise value matters for the timeline, but the qualitative outcome is the same for any value below -1. And the outcome is the Big Rip. In the phantom energy scenario, the density of dark energy does not remain constant as the universe expands. It increases. More space means more dark energy, and the dark energy in each cubic centimeter of space also grows denser over time. This creates a runaway feedback loop. More dark energy means faster expansion. Faster expansion creates more space. More space means even more dark energy. Even faster expansion. The acceleration does not plateau, it escalates. It feeds on itself, growing without limit. At first, the effects are indistinguishable from a cosmological constant. For billions of years, the universe looks the same. Galaxies drift apart. The expansion accelerates. The differences between phantom energy and a cosmological constant are too subtle to detect with anything but the most precise instruments. But over time, the differences grow. The acceleration becomes fiercer. The expansion becomes more violent. And eventually, the growing dark energy overwhelms everything. Here is the timeline, roughly, for a phantom energy scenario with W equal to -1.5, starting from today. The specific numbers shift depending on the exact value of W, but the sequence of events is always the same. Roughly 22 billion years from now, the expansion of space becomes strong enough to overcome the gravitational binding of galaxy clusters. Today, galaxy clusters are the largest gravitationally bound structures in the universe. Thousands of galaxies held together by their mutual gravitational attraction, orbiting their common center of mass, bound as surely as the Earth is bound to the Sun. But in the phantom energy scenario, the dark energy pervading the space within these clusters grows strong enough to overpower that binding. The clusters come apart. Galaxies that have been gravitationally bound companions for billions of years are torn from each other and flung into the expanding void. About 60 million years before the end, the expansion rips apart individual galaxies. The Milky Way, with its hundreds of billions of stars held together by gravity, is torn to pieces. Stars are stripped from the galaxy and scattered into expanding space. The gravitational glue that held the galaxy together for over 13 billion years is overwhelmed by the relentless growth of dark energy. The night sky, once filled with the glow of the galactic band, goes empty. About 3 months before the end, solar systems are destroyed. The expansion becomes fierce enough to overpower the gravitational bond between a star and its planets. Earth, if it still existed, would be ripped away from the sun. Planets are flung outward into darkness, untethered from their parent suns. Every solar system in the universe dissolves simultaneously. Their gravitational bonds snap by the escalating expansion of space. About 30 minutes before the end, planets themselves are torn apart. The rocky body of a world like Earth, held together by the electromagnetic forces binding its atoms and molecules, is overwhelmed by the expansion. The planet fragments. Mountains, oceans, continents, all of it ripped to pieces by the stretching of space within the planet itself. In the final fraction of a second, atoms are destroyed. The expansion becomes strong enough to overwhelm the electromagnetic force holding electrons to nuclei and the strong nuclear force binding protons and neutrons together within atomic nuclei. Atoms are ripped apart into their constituent particles. Then even those particles might be torn apart if the escalation continues. Quarks separated from one another. The very fabric of matter shredded beyond recognition. And then space itself may tear. The expansion rate diverges to infinity in finite time. The scale factor of the universe, the mathematical quantity describing how much space has stretched since the Big Bang, reaches infinity. Space-time itself is ripped apart. This is the big rip. Not a slow fade, not a gentle cooling. A violent, total destruction of everything that exists. From the largest galaxy clusters down to the smallest subatomic particles occurring everywhere in the universe simultaneously in a finite amount of time. The Big Rip is terrifying because it is final and absolute in a way that heat death is not. Heat death leaves behind a cold, empty universe, but that universe still exists. Space is still there. Time still passes. Particles still drift. In principle, quantum fluctuations over unimaginable timescales could create momentary pockets of structure, fleeting and vanishingly improbable, but not strictly impossible. Heat death is eternal emptiness, but it is not annihilation. The Big Rip is annihilation. There's nothing left. No space, no time, no particles, no fields, no possibility of anything ever happening again. The universe does not merely become empty, it ceases to exist in any meaningful sense. Now, it is important to emphasize that the Big Rip is not a prediction. It is a possibility. It happens only if W is less than -1, and current observations are consistent with W being very close to exactly -1. We cannot yet distinguish between a true cosmological constant and a phantom energy with W just slightly below -1. The error bars on our measurements of W still straddle the critical boundary. The universe might be heading for heat death or for the Big Rip, and right now, we cannot tell which. There is also a third possibility. What if W is greater than -1? In some quintessence models, the field's energy density gradually decreases over time. The accelerating expansion eventually slows. The universe still expands forever, but the acceleration tapers off. The future still ends in isolation and cold, but the process is even gentler and the timeline stretches longer. Some quintessence models allow for even more exotic possibilities. The field could evolve in ways that change the sign of its pressure. Dark energy could weaken, vanish entirely, or even reverse, becoming attractive rather than repulsive. If dark energy reversed, the expansion would eventually slow, stop, and the universe would begin to contract. Gravity would reassert itself. Galaxies would fall back together. The cosmos would compress, heating up as it shrank, until everything collapsed into a state resembling the conditions of the Big Bang, a scenario called the Big Crunch. Some models propose that a big crunch could trigger a new Big Bang, a bounce, creating a cyclic universe that expands and contracts repeatedly for all of eternity. These are fascinating possibilities, but they remain highly speculative, and current observations do not favor them. What the observations do tell us, consistently and from multiple independent sources, is that W is very close to -1. The data is compatible with a true cosmological constant, but it is also compatible with quintessence or phantom energy, as long as the deviation from -1 is small enough to hide within our measurement uncertainties. Narrowing those uncertainties, pinning down the value of W with greater precision, determining whether it is exactly -1 or slightly different, and whether it changes over time, is the central quest of observational cosmology in the 21st century. The stakes could not be higher. This is not an abstract parameter in an equation that matters only to theorists. This number, W, determines whether the universe ends in silence or in violence, whether the cosmos fades into cold, dark, eternal emptiness, its structures slowly dissolving over trillions upon trillions of years, or whether it tears itself apart in a catastrophic rip that destroys atoms and spacetime itself in a finite, measurable amount of time from now. Think about what that means. The fate of every galaxy, every star, every planet, every atom, every force of nature, everything that exists or ever will exist, hinges on whether a single number equals exactly -1 or is slightly different. The margin between an eternal, quiet emptiness and total cosmic annihilation might be a difference of 0.1, or 0.01, or 0.001. A difference so small that it takes the most precise instruments ever built, observing the most distant objects in the universe, analyzing data accumulated over decades, just to begin distinguishing between the two. We are living inside a universe whose ultimate fate is genuinely uncertain. Not uncertain in the sense that we have not bothered to figure it out. Uncertain in the sense that the answer depends on measurements we have not yet been able to make with sufficient precision. The universe is expanding. The expansion is accelerating. Something with negative pressure is driving that acceleration. We can measure how much dark energy there is. We can measure its effects on the expansion. But we cannot yet determine whether it is constant or changing, whether it will remain as it is or grow stronger or weaken, whether the cosmos ends in a whisper or a scream. And that is why the next generation of experiments matters so much. Somewhere in the data streaming back from telescopes, scanning the sky at this very moment, in the patterns of light from distant galaxies, in the subtle imprints left on the cosmic microwave background, in the way matter clusters across billions of light years, the answer is hiding. The value of W is encoded in the structure of the universe itself. We just need instruments precise enough to read it. We know dark energy exists. We know it makes up roughly 68% of the total energy content of the universe. We know it exerts a negative pressure that drives the expansion of space to accelerate. We know it has been the dominant force shaping the large-scale evolution of the cosmos for the past several billion years. What we do not know is what it is. We do not know whether it is a fixed cosmological constant or a dynamic field that changes over time. We do not know the precise value of its equation of state parameter W, or whether W is evolving. And until we pin down those answers, we cannot determine the ultimate fate of the universe. So how do you study something you cannot see, cannot touch, and cannot detect directly? You study its effects. Dark energy does not emit light. It does not absorb light. It does not interact with matter in any way that our detectors can register. But it shapes the geometry of the universe. It dictates how fast space expands at every epoch of cosmic history. It influences how matter clusters together over billions of years. And those effects leave fingerprints, subtle, faint, but measurable fingerprints imprinted on the structure of the cosmos itself. If you know where to look, and if your instruments are precise enough, you can read those fingerprints and reconstruct the properties of the invisible force that left them. 3 independent methods form the backbone of modern dark energy research. Each one probes a different aspect of the universe's expansion history. Each one is subject to different systematic uncertainties. And when all 3 point to the same answer, as they increasingly do, the result carries a weight that no single method could achieve alone. The first method is the one that started it all. Type 1a supernovae. We have already discussed how these exploding white dwarfs serve as standard candles, objects of known intrinsic brightness whose apparent dimness reveals their distance. The original 1998 discovery relied on a few dozen carefully measured supernovae. Since then, the sample has grown enormously. Modern surveys have catalogued hundreds of Type 1a supernovae spanning a wide range of redshifts, from relatively nearby galaxies to galaxies whose light has been travelling for more than half the age of the universe. The principle remains the same. You find a Type 1a supernova. You measure its apparent brightness and its redshift. The brightness tells you how far away it is. The redshift tells you how much space has expanded while the light was traveling. By comparing distance and redshift for many supernovae at many different distances, you can reconstruct how the expansion rate of the universe has changed over time. If the expansion was decelerating in the past and began accelerating more recently, the relationship between brightness and redshift will show a specific pattern. That pattern depends on the properties of dark energy. Different values of W produce slightly different patterns. By measuring the pattern with enough precision across enough supernovae, you can constrain W. Modern supernova surveys have become extraordinarily sophisticated. Telescopes scan large areas of the sky repeatedly, night after night, automatically comparing images to detect new points of light that might be supernovae. Spectrographs confirm the type and redshift of each candidate. Sophisticated software corrects for every known source of error, from the absorption of light by dust in the host galaxy to the subtle differences between individual supernovae. These systematic uncertainties that plagued the original 1998 measurements have been dramatically reduced, but they have not been eliminated entirely. Supernova cosmology still depends on our understanding of the explosions themselves, on our ability to correct for dust, on our confidence that Type 1a supernovae at high redshift behave the same way as nearby ones. These are challenges that ongoing research continues to address. The second major method for studying dark energy uses something far older than any supernova. It uses the oldest light in the universe, the cosmic microwave background. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral atoms. Before this moment, light could not travel freely through the hot, dense plasma. But when the plasma became neutral gas, light was suddenly free to travel unimpeded. That first light has been traveling through space ever since, stretched by the expansion of the universe from its original short wavelength glow into the long wavelength microwaves we detect today. This is the cosmic microwave background, a faint, uniform glow of microwave radiation filling all of space, coming from every direction, a snapshot of the universe as it looked 380,000 years after the Big Bang. This ancient light was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey who were trying to eliminate an annoying background hiss from their antenna and could not figure out where it was coming from. That hiss turned out to be the afterglow of creation itself. They won the Nobel Prize. The cosmic microwave background is not perfectly uniform. It contains tiny temperature fluctuations, variations of roughly 1 part in 100,000 from one patch of sky to another. These fluctuations are the imprints of density variations in the early universe, regions that were slightly denser or slightly less dense than average. Those density variations are the seeds from which all structure in the cosmos eventually grew. Slightly denser regions attracted more matter through gravity over millions and billions of years, eventually collapsing into galaxies and galaxy clusters. Slightly less dense regions became the voids, the great empty spaces between cosmic structures. The pattern of these fluctuations is not random. It has a specific statistical structure that depends on the composition and geometry of the universe. The size of the hot and cold spots, the relationship between spots of different sizes, the way temperature variations correlate across different angular scales on the sky, all of this encodes information about the fundamental parameters of cosmology. And dark energy is one of those parameters. Here is why. The pattern of fluctuations in the cosmic microwave background depends on the geometry of the universe. The geometry, in turn, depends on the total energy density of everything the universe contains: matter, radiation, and dark energy. If you know the total energy density, and you independently measure how much is in the form of matter and radiation, you can determine how much must be in the form of dark energy. The cosmic microwave background gives you the total budget of the universe. Other measurements tell you how much of that budget is accounted for by matter. Whatever is left over must be dark energy. Satellite missions have mapped the cosmic microwave background with extraordinary precision. The WMAP satellite, launched in 2001, produced detailed all-sky maps that confirmed the universe is geometrically flat and that dark energy accounts for roughly 68% of its total energy content. The European Space Agency's Planck satellite, launched in 2009, improved on WMAP's measurements with even greater precision, pinning down cosmological parameters to percent-level accuracy. These measurements are consistent with a cosmological constant, The value of W derived from the cosmic microwave background alone is compatible with -1. But the cosmic microwave background by itself cannot determine W with enough precision to distinguish between a cosmological constant and a slowly evolving quintessence field. For that, you need to combine it with other measurements. The third major method is perhaps the most elegant. It uses a feature built into the structure of the universe itself, a cosmic ruler frozen into the distribution of matter across billions of light years. It is called baryon acoustic oscillations. To understand baryon acoustic oscillations, go back to the early universe, before the cosmic microwave background was released. In the hot, dense plasma that filled the universe during its first few 100,000 years, matter and radiation were locked together. Photons scattered constantly off the free electrons, and the electrons were bound to the protons by electromagnetic forces. Any region slightly denser than average would trigger a wave. The extra gravity pulled matter inward, but the radiation exerted outward pressure. The result was an acoustic wave rippling outward through the plasma at roughly half the speed of light. These sound waves propagated outward from every overdense region in the early universe, expanding as spherical shells of compressed matter and radiation. They traveled for about 380,000 years, until the universe cooled and the plasma became neutral gas. At that moment, the photons decoupled from the matter and streamed away freely, becoming the cosmic microwave background. And the sound waves froze. They stopped propagating. The shells of compressed matter were locked in place, imprinted on the distribution of matter across the cosmos. The radius of these frozen shells, the distance the sound waves traveled before they stopped, is about 500 million light years in today's expanded universe. This distance is called the sound horizon, and it shows up as a subtle but measurable feature in the distribution of galaxies. If you survey a large volume of the universe and measure the distances between millions of pairs of galaxies, you find a slight statistical excess of galaxy pairs separated by roughly 500 million light years. There are slightly more pairs at this distance than you would expect by chance. This is the baryon acoustic oscillation signal, a preferred scale stamped into the cosmos by sound waves in the primordial plasma. This preferred scale is a standard ruler. Just as type 1a supernovae provide a standard candle of a known brightness, baryon acoustic oscillations provide a standard ruler of known physical size. You know how big the ruler truly is because you can calculate it from the well-understood physics of the early universe. And you can measure how big it appears at different redshifts by surveying galaxies at different distances. By comparing the ruler's known true size with its apparent size at each redshift, you can determine how the universe has expanded at different epochs. Different expansion histories produce slightly different apparent sizes for the ruler at each redshift. And the expansion history depends on dark energy's properties. This method is beautifully complementary to supernova. Supernova measure distances using brightness. Baryon acoustic oscillations measure distances using geometry. The two methods have completely different systematic uncertainties. Dust, which can bias supernova measurements, has no effect on baryon acoustic oscillations. The internal physics of exploding white dwarfs, which must be carefully modeled for supernova cosmology, is irrelevant to the galaxy distribution measurement. When both methods give the same answer, the result is far more robust than either method alone. Measuring baryon acoustic oscillations requires surveying enormous volumes of the universe. You need precise positions and redshifts for millions of galaxies spread across billions of light years. This is a monumental observational challenge. It requires massive telescopes, sophisticated spectrographs capable of measuring thousands of galaxy redshifts simultaneously, years of observing time, and extraordinary computational power to analyze the resulting datasets. These three methods, Type 1a supernovae, the cosmic microwave background, and baryon acoustic oscillations, form what cosmologists sometimes call the three pillars of dark energy research. Each one constrains the properties of dark energy from a different angle. Each one has different strengths and different weaknesses. And when you combine all three, the constraints tighten dramatically. The combined data tells us that W is very close to -1. The universe is behaving almost exactly as a cosmological constant would predict. But almost is not exactly. And the difference between almost and exactly is where the most exciting physics might be hiding. This brings us to the experiments that are working right now, at this very moment, to push the precision further than it has ever been pushed before. Two missions in particular are poised to transform our understanding of dark energy over the coming years. The first is the Dark Energy Spectroscopic Instrument, known by its initials DESI. This instrument is mounted on the 4-meter Mile telescope at Kitt Peak National Observatory in Arizona, and it represents the most ambitious spectroscopic survey of the universe ever attempted. DESI's goal is to measure the redshifts of roughly 40 million galaxies and quasars over a 5-year observing campaign, mapping the 3-dimensional distribution of matter across 11 billion years of cosmic history. The instrument itself is a marvel of engineering. Its focal plane contains 5,000 tiny robotic fiber positioners, each one capable of independently swiveling to point at a specific galaxy. In a single exposure, DESI can simultaneously measure the spectra and redshifts of 5,000 objects. Over the course of a night, it can observe tens of thousands of galaxies. Over its 5-year survey, it will build a 3-dimensional map of the universe containing more galaxies than all previous spectroscopic surveys combined. This map is designed to measure baryon acoustic oscillations with unprecedented precision at many different redshifts. By slicing the map into bins at different distances and measuring the baryon acoustic oscillation scale in each bin, DESI can track how the expansion rate of the universe has changed over time with a level of detail no previous experiment has achieved. This allows a far more sensitive measurement of W and, crucially, of whether W changes over time. In early 2024, the DESI collaboration released its first-year results based on data from roughly 6 million galaxies and quasars. The results sent a ripple of excitement through the cosmology community. The baryon acoustic oscillation measurements, when combined with supernova data and cosmic microwave background observations, hinted that dark energy's equation of state parameter might not be constant. The data showed a mild preference for models in which W changes over time, starting at values below -1 at earlier cosmic epochs, and evolving toward values above -1 more recently, as though dark energy were gradually weakening. If confirmed, this would rule out a simple cosmological constant. Dark energy would not be lambda. It would be something dynamic, something evolving, something we do not yet have a name for, but it is essential to be cautious. The hint is intriguing but not yet conclusive. The statistical significance is not strong enough to claim a discovery. It is a suggestion, a whisper in the data, not a shout. The DESI team has been careful to emphasize that more data is needed. The survey is still ongoing. Each additional year of observations will add millions more galaxies to the map, tightening the constraints, reducing the uncertainties, and either strengthening the hint into a discovery or dissolving it into statistical noise. The second transformative mission is Euclid, a space telescope launched by the European Space Agency in July 2023. Euclid is designed to survey roughly 1/3 of the entire sky, mapping the shapes, positions, and redshifts of over 1 billion galaxies across 10 billion years of cosmic history. It operates from a gravitationally stable point in space about 1.5 million kilometers from Earth, far from the atmospheric distortion and light pollution that limit ground-based telescopes. Euclid uses two complementary techniques to study dark energy. The first is baryon acoustic oscillations, similar to DESI but from space, with different systematics and a different survey strategy. The second is a technique called weak gravitational lensing. This method exploits the fact that massive structures in the universe, galaxy clusters, filaments of dark matter, bend the light from more distant galaxies as it passes through. This bending distorts the shapes of the background galaxies very slightly, stretching them into faint ellipses aligned with the foreground mass distribution. By measuring the shapes of hundreds of millions of galaxies and statistically analyzing the patterns of distortion across the sky, Euclid can map the distribution of all matter, including the invisible dark matter, across enormous volumes of the universe. This matter distribution, in turn, depends on how the universe has expanded, which depends on dark energy. Weak lensing is extraordinarily challenging. The distortions are tiny, far smaller than the natural ellipticity of galaxies themselves. You cannot measure the lensing effect on any individual galaxy. You can only detect it statistically by averaging over millions of galaxies and looking for correlations in their shapes that would not exist if lensing were absent. This requires exquisitely precise measurements of galaxy shapes, which in turn requires exquisitely precise knowledge of the telescope's own optical properties. Any distortion introduced by the telescope itself must be meticulously characterized and removed. From space, Euclid avoids the blurring caused by Earth's atmosphere, making its shape measurements far sharper and more reliable than those from ground-based telescopes. Together, DESI and Euclid represent a new era in dark energy research. They are not just incrementally better than previous experiments. They are qualitatively different, mapping the universe with a precision and depth that was unthinkable a generation ago. Within the next several years, as their datasets grow and mature, they will either confirm that dark energy is a cosmological constant, settling the question with a level of precision that leaves no room for doubt, or they will reveal that dark energy is something more complex, something dynamic, something that changes over time in ways we need new physics to explain. Other experiments are contributing as well. The Vera C. Rubin Observatory in Chile, expected to begin its primary survey in the mid-2020s, will conduct the legacy survey of space and time, imaging the entire visible southern sky repeatedly over 10 years. It will discover hundreds of thousands of Type 1a supernovae, vastly expanding the sample available for distance measurements. It will also perform its own weak lensing measurements, complementing Euclid's space-based data with deep, ground-based observations. The sheer statistical power of these combined datasets will drive measurement uncertainties down to levels where even tiny deviations from a cosmological constant become detectable, ground-based cosmic microwave background experiments are also pushing forward. New observatories are deploying thousands of detectors at high-altitude sites in Chile and at the South Pole, measuring the polarization of the cosmic microwave background with sensitivity that previous generations of experiments could not approach. These polarization measurements constrain cosmological parameters in ways that complement galaxy surveys and supernovae, further tightening the net around dark energy's properties. Think about what is happening here. Humanity is deploying an interlocking web of instruments on mountaintops, in deserts, at the South Pole, in orbit around the Sun, each one designed to measure a different fingerprint of the same invisible force. Each instrument has different strengths, different blind spots, different sources of error, but they are all asking the same question. Is W exactly -1, or is it something else? Does dark energy change over time, or does it remain constant? And the answer, when it comes, will not rest on any single measurement. It will rest on the convergence of independent lines of evidence, each one cross-checking the others, each one closing off a different escape route for systematic error. This is how science works at its best. Not a single experiment delivering a single verdict, but a web of evidence tightening around the truth from every direction simultaneously. And the truth, they are closing in on matters more than almost any other question in science. Because dark energy is not merely a curiosity for physicists. It is the dominant component of the universe. It controls the expansion. It determines the geometry. It dictates the fate of every structure that exists, or ever will exist. If the experiments confirm that W equals -1, then the cosmological constant is the answer. Dark energy is a permanent, unchanging feature of spacetime. The universe will expand forever, accelerating into eternal isolation. Galaxies will drift beyond each other's horizons, stars will burn out, matter will decay, black holes will evaporate, and the cosmos will fade into a cold, dark, silent emptiness that lasts forever. This is not a theory. It is not speculation. It is the mathematically inevitable consequence of a universe dominated by a cosmological constant. The only question is whether the cosmological constant is truly what we are dealing with. If the experiments reveal that W changes over time, everything opens up. Dark energy becomes a dynamic field with properties we need to discover and understand. The future of the universe depends on how that field evolves. If it weakens, the acceleration may taper off, and the universe may settle into a gentler, eternal expansion. If it strengthens, the acceleration grows fiercer, and the Big Rip becomes a possibility. The violent destruction of all structure down to the subatomic scale. We would need to measure the evolution of W with enough precision to determine which trajectory the universe is on, and even then, the answer might depend on physics we have not yet discovered. Either way, the answer tells us something profound about the nature of reality. If dark energy is a cosmological constant, we must confront the cosmological constant problem, the 120 order of magnitude discrepancy between quantum field theory's prediction and observation. That discrepancy is a signpost pointing toward new physics, toward a deeper understanding of the relationship between quantum mechanics and gravity that we have not yet achieved. If dark energy is quintessence, we must identify the field, understand its energy landscape, and explain why it has the properties it does. Either path leads to new physics. Either path leads to a deeper understanding of the universe, and either path begins with the measurements being made right now. Consider where we stand in the story of human understanding. For most of history, we did not know the universe was expanding. For most of the 20th century, we assumed the expansion was decelerating. In 1998, we discovered it was accelerating. In the years since, we have confirmed the acceleration with multiple independent methods. We have measured the amount of dark energy filling the universe. We have constrained its equation of state to be very close to -1. And now, for the first time, we have instruments precise enough to ask the next question. The question that determines everything. Is dark energy constant, or does it change? The universe has been expanding for 13.8 billion years. Dark energy has been the dominant force driving that expansion for roughly the past 5 billion years. In that time, it has reshaped the cosmos, accelerating the expansion, thinning out the matter, pushing galaxy clusters apart, and setting the universe on a trajectory toward a future that will look nothing like its past. Every galaxy you can see in the night sky, every point of light scattered across the darkness, every distant cluster glowing faintly at the edge of visibility, all of them are being carried away from us by the stretching of space. And that stretching is getting faster. 68% of everything that exists is something we discovered only a quarter century ago. Something we still cannot explain. Something that operates through a mechanism, negative pressure, that defies ordinary intuition. It is the dominant force in the cosmos. It will determine how the story ends. And we are the first generation of humans with instruments capable of interrogating it directly, of measuring its properties with the precision needed to distinguish between a universe that fades quietly into eternal darkness and one that tears itself apart. We are living at a remarkable moment. The universe has handed us its deepest mystery. It has shown us that the thing that controls everything, the force shaping the largest structures in existence, the energy that determines whether the cosmos ends in silence or catastrophe, is something we do not understand. And then it has given us just barely enough clues, imprinted in the faint glow of the oldest light, in the clustering of millions of galaxies, in the dying flares of exploding stars, to begin figuring it out. The answer is written in the structure of the universe itself. And right now, tonight, telescopes on mountaintops and satellites in deep space are closing in on the truth about what dark energy is and what it means for the fate of everything. We may be small, but we are asking the right questions. And for the first time, we have the tools to answer them.